Yeah, thanks for the introduction. I'm Daniel here from RPI. I'm soon moving to Goddard, and yeah, I'm supposed to give the warm-up talk about planetary atmospheres right after lunch, so it's probably more a wake up or avoiding that you fall asleep after lunch talk, so I keep it really basic. I hope that I even get to atmospheres. Maybe I'm just talking about planets in general, so let's see how that works. So if you saw a talk of me before, maybe last year at AbGradCon, I love to start my astrology talks with that old Hindi or Thai legend about the blind man and the elephant, and as that story goes, a couple of blind men find an elephant and try to figure out what that thing is, and the first guy, checks out the tail and says, yeah, for me that feels like a brush, and the second guy touches the side and he's like, yeah, I don't know, but for me that feels more like a rock, and the third guy checking out the leg and he's like, yeah, for me that feels like a tree or something, and I think that's kind of a nice analogy to astrobiology. So we all are kind of blind on our fields alone, and just as we connect our knowledge, we really can start answering that question about life in space. And after Montreal last year, there's actually a little bit more. Like, I came to the conclusion there's actually even more to that story. It's not that we are just blind, we're also kind of, deaf in a sense. So if you look at all these bubbles here, if we start talking in the lingo of our field, you pretty soon lose the other people. So if I, as an astronomer, talk about late-type main-sequence stars, I'm pretty sure that not everybody around knows what a late-type main-sequence star is, even though that's really astronomy 101. And I guess for the other fields, if you talk about olivine serpentinization, which I can't even pronounce, really, so, which is 101 geology, supposedly, but I'm pretty sure that not everybody knows that. So in that sense, we also have to zoom out a little bit, maybe leave away some of the gory details and really focus on the big picture if you want to explain it cross-disciplinary to other guys from other fields who might not have that background knowledge and the 101 knowledge that we have in our own fields. And that whole question of astrobiology and life on other planets, if we are alone in the universe, is actually a really, really old question. So started with Epicurus about 2,500 years ago, Bruno, Newton, really big minds in history thought about that problem or thought about the idea, are there other planets, is there life outside, are we alone? And right now is probably the coolest time ever to be involved in that kind of studies. We are finding exoplanets, actually amateurs finding exoplanets. We are finding exoplanets in our closest solar neighborhood. We find planets that are potentially habitable. We can show that salt on Mars can turn ice into liquid water. We are hopefully getting a mission to Europa soon, so it's really, really exciting time to work in this field. And one example is the field of exoplanets, where I'm coming from. We are finding exoplanets in really, really large numbers right now, and this is pretty much the actual number of exoplanets we know right now, and this is basically a size, that doesn't work. It's a size versus temperature diagram here. So you're going from really small ones, Mercury-sized planets, towards Jupiter-sized planets, and then from hot planets really close into the host star to relatively cold planets farther out. And as you can see, the first planets that we found were these hot Jupiters, obviously because they are bigger, they have a bigger signature, they are hotter, they emit more photons, so these are actually the easiest ones to find. And that's also what you can see, a kind of an observational bias, so that's not the absolute numbers of planets that we find. It's the reason that we don't find these small cold ones is just because they are just too hard to find. It's not that they are less than the others. So this is definitely an observational bias in this field. And obviously we are interested in these potentially habitable exoplanets, which is kind of a wishy-washy definition. So you all know that concept of the habitable zone, which I'm also going to talk about later, which is maybe a little bit too geocentric because things we talk about Europa and Titan, which are obviously not in the habitable zone, but still are really interesting targets to look for life. So I'm going to talk a little bit about these borders up here and down there in terms of temperature. But it's also interesting to talk about the size. So at a certain size, the planet might be too small to harbor life, and at some point it might be too big and become a gas giant, which is maybe also not the best place to think about life. And actually have the same plot for our solar system. So these are the solar system bodies that we know today, and you see it's really different from the zoo of exoplanets that we are finding. So we have 2 potentially habitable planets, Earth, Mars here, then we have Venus, which is slightly out of this habitable place here, and then we got 4 really cold gas giants far out, and lots of these small moons around here in the cold zone. And if you compare that and go back, one interesting kind of planets that we find is a huge group of so-called super-Earths, mini-Neptune planets, which we don't have an analog, so it's totally empty in our solar system, but it's one of the class of exoplanets where we actually find the most right now. So this is really an interesting question for us right now, and I'm going to talk a little bit more about that. And yeah, and the other thing, as I said already, is mostly an observational bias, just because our detection methods are not good enough yet to find these small ones farther out. So this is where we are looking for life, either in our solar system or in exoplanets, maybe in the future. So as I mentioned before, this concept of habitability, the habitable zone, you probably all heard about that. That's that so-called Goldilocks zone where it's warm enough and not too cold to eventually have liquid water, which we think is the base of life. And you see here in our solar system, we have Earth somewhere in the center of it, and Mars somewhere on the colder side, and Venus somewhere on the warmer side. And depending on that definition of the habitable zone, they are right on the edge or maybe slightly out. And then, as I mentioned before, we also have objects like Europa, which are obviously not in that habitable zone, in that classic definition of the habitable zone, but still might be good targets to look for life. And one other interesting class, and this is the one that we astronomers in exoplanets are mostly interested in, are these close-in planets around late-type stars. So these late-type, fainter and much smaller stars, because they're just easier to detect for us. And for those who've been last year at Montreal, I gave a talk about these. So these are the most interesting guys for us right now. So the question is, what makes a difference in this zone? So how can planets keep their habitability over a long period of time, and why, for example, is Mars not habitable anymore, and why is Venus as hot as it is? And oh yeah, right. And so to already prepare you for the next talk, so we have a talk by Eric Larson about the 3-dimensional modeling of Titan's organic haze with implications for the early Earth. So a talk right here, far away from the habitable zone, but apparently also astrobiology, and a talk by Thompson Fisher about modeling of the Venusian atmosphere as a microbial habitat. So again, not really in the habitable zone, but apparently astrobiology. So, and the key here is, as the title says, the atmosphere. So if you just compare Mars, Earth, and Venus, they have totally different atmospheres. Venus has a really thick atmosphere with 96% of CO2. It's really hot due to that greenhouse effect caused by all the CO2 in the atmosphere. At Earth, we are slowly increasing the CO2 and also might run into the danger to produce something like Venus in the future if we don't take care of that. And then we have Mars with that really thin atmosphere, which we heard this morning, which is therefore really cold because it doesn't have that thick atmosphere that keeps the heat in the greenhouse effect. And greenhouse effect is really one of the central things that I want to talk about. So if you compare these temperature pressure profiles or altitude temperature profiles of Mars, Earth, and Venus, you see that Venus is really hot close to the ground and then cooling down up there. Then you know Earth with our temperature pressure profile here, and then Mars, which is even colder. And if you look on the y-axis here, you can see that without the greenhouse effect, all 3 planets would actually be colder than would be frozen water everywhere. So it's really the greenhouse effect to keep the atmosphere somehow habitable, or in the case of Venus, it's heating it up too much to be not habitable anymore. So these greenhouse effects are really important to keep a sustainable atmosphere for life. And then I'm coming back to the super-Earths versus mini-Neptune, so this kind of border, not in temperatures, but in size of the planet. So as I mentioned before, we are finding huge amounts of these planets right now, which we don't have an analog in the solar system. And the big question that we try to solve, are these medium-sized planets more like big rocky Earths, or are they more like small gas planets like a mini Neptune. And this is an important question because obviously it's much easier, or it's probably more common to have life on planets like that than on big gas giants. So right now we are trying to find the border in mass and size where we can distinguish between rocky planets and these mini Neptunes, because that immediately gives us a number, or changes the number of potentially habitable worlds, and that whole Drake equation thingy about how many other potential civilizations might there be. And just a quick introduction to the science that I'm doing. So how are we analyzing the atmospheres of these extrasolar planets? And the technique that I'm used is the so-called transit method. You probably all heard about it. For example, the Kepler mission is using that. And for these systems, we are lucky enough to look edge-on these systems. And in most of the cases, we have a primary transit where the exoplanet crosses across the disk of the star, and the outer atmospheric ring is absorbing some of the light. And then we, in most of the cases, also have a secondary eclipse where the planet disappears behind the star, and we got a little dip in the light curve, which is actually the photons from the planet missing during this phase. And typically, these light curves look like that. So you got like that dip, either in primary or secondary transit, depending what you're looking at. And what we do is spectrophotometry. So we just not observe it at one wavelength at a time, but try to use spectrographs or multiple imagers to observe these light curves at many wavelengths at the same time. And if you, for example, look at an absorption line of a certain molecule that you expect in the atmosphere, that transit line would be deeper because your atmospheric ring would be projected, produce a bigger radius in that line than it would in a line where the light can pass by. So that's kind of the idea how we are getting exoplanet spectra. And then in this case, each of these light curves would represent a spectral data point at that certain wavelength where that light curve was observed. And then we usually ask our colleagues who produce exoplanet models. In this case, there's a model with water, which is that blue one here, which doesn't really fit our data. Then we put some methane in the mixture, which gives us that green data, or green model, which kind of fits the data, but not really well. But just as we also put CO2 in our mixture, we get a spectrum that kind of fits our observational data. And usually if you hear this and that molecule detected in exoplanet, this is most of the time the technique that we use to characterize these exoplanet atmospheres. And from these spectra, we can talk about the atmospheric composition, which molecules are present. We can talk about the atmospheric structure, so which temperature pressure profile was used to produce these models. We can also talk about the formation history, so depending where in that protoplanetary disk the star is formed, it contains different composition than if it would be produced in another part of the disk. And the final goal, also in the context of astrobiology, is of course with next generation instruments to eventually look for biomarkers. And this is the big question where I think we need the whole astrobiology community to answer that question: what is really a biomarker for remote detection? So at least for these exoplanets, we only see one point. So we can't spatially reduce them. We obviously can send a rover there. So the only thing we can do is remote detection. And since it's only a dot, we only get one-dimensional spectra. So the key here is to find biomarkers that we all agree on are actual biomarkers. And this is also a topic of some of the talks. So you can imagine a planet like Earth. There are so many systems interacting. It's not just the biosphere, it's the lithosphere producing, outgassing from volcanic activity. We have the hydrosphere, the ocean absorbing stuff and emitting stuff again. You got the upper atmosphere where you get lots of photochemistry depending on what radiation gets in. So we really have to look at that whole system to see which particular signatures just the biosphere does. So in this case, this is really one of these elephants where we have to connect all parts of astrobiology to understand that whole system and to eventually find out which of these signatures are actual biomarkers. And here we also have two talks in the next session, one by Chester Harman about oxygen false positives in planetary atmospheres. So oxygen obviously is on the first view an interesting biomarker because it's produced by photosynthetic organisms, but there are also abiotic processes like hydrogen escape and stuff like that that could produce oxygen false positives, and I think he's talking about stuff like that. And then we have the talk by Eugenio, which is the next talk. He looks at it more from the theoretical side and looking at disequilibrium and the effect of life on planetary atmospheres. So in a broader sense, life is living off temperature gradients or chemical gradients because it needs to get the energy from somewhere. And at the same time, life produces a disequilibrium in the atmosphere, and that might be a more general way to look at biomarkers. And yeah, that's going to be the next talk, and that was my warm-up talk. Thank you.
Any questions real quick before we move on? All right. Oh, there we go.
When you look at the biosignatures in the atmosphere, would you be able to distinguish different ones, or do you already have a database to compare it to? When you in the atmosphere.
So you mean how we produce these model spectra?
Yeah.
Yeah, they usually use libraries like Hydran, for example, or there's also that ExoMol from London who collect specifically molecular lines at the certain temperatures of the planets that we're using, and then they put radiative transfer models, sometimes even 3D dynamical models, and then put all that together, steer it, and then simulate the light going from the star through it, and then at the end you get these spectra. But the base is, of course, like molecular databases or laboratory spectra like Hydran and stuff like that. And we really depend on them, so it's like there's some, especially at these temperatures of hot Jupiters that are not really, astrobiology topic, but at these temperatures we really miss some of the important molecules. So this is really a big theoretical work that we as exoplanet scientists have to rely on and wait for people producing these model spectra.
Danny, I think I made you the same question back at your talk at the University of Michigan, but I forgot. How exactly did you define the habitable zone? It's based on, you said before, based on temperature, based on, it's like, there's like a formal definition, like the...
Maybe Chester can answer it even better, so he's the expert on the habitable zone. So I think it's like the definition of life. I think there's not really like a clear definition that everybody really agrees on. So it's like that basic idea, yeah, it's the zone where water is liquid, but then, the outer and inner edge are kind of depending on your definition might vary a little bit. So as I mentioned before, in some definitions, Venus is in the habitable zone or Mars is in the habitable zone. In other definitions, it's not. And as I mentioned before, I think it's typical human mistake to approach that habitable zone with like a geocentric, tunnel view on it. So I mean, as I showed, like Europa, Titan is totally out of the habitable zone, and there are mechanisms like tidal heating that can heat up bodies farther out into temperature regimes that are habitable. So, yeah.
All right, let's thank Daniel again.